Okay, we're now moving into conservation of energy problems. So, just overall energy analysis. And the main equation that's guiding us here is the change in mechanical energy is equal to the sum of works done by our non conservative forces. Okay, so change in mechanical energy here, final minus initial, is equal to the sum of the works done by non-conservative forces. So, non-conservative forces, sometimes we'll throw students, what are non-conservative forces? It's much easier to describe what conservative forces are and say that everything else is non-conservative. So, our conservative forces that we have in this class are weight, otherwise known as gravitational force, and spring force or elastic force. So weight and spring force. Every other force you encounter in here is a non-conservative force. So think about all the other forces we see, tensions and normal forces and frictional forces and applied forces. Those are all non-conservative forces. Again, the only conservative forces are gravitational force and spring force. And that's because conservative forces are forces that when they do work, can store energy. They can put energy in a form that we call potential energy, which is basically just a stored form of energy that you can use later. And energy can be stored in the gravitational field if you lift something up. Energy can be stored in a spring if you deform the spring, right? So that's it. Those are our only two conservative forces. Okay, everything else is non-conservative. What else do we know here? We have some different types of mechanical energy. We've got kinetic energy, which we've worked with 1/2 mv squared, and then gravitational potential energy, mgy. There's also elastic or spring energy. I'm not going to use that here because there's no spring in this problem. So we'll leave it. We're also going to be using works since we need to find the works done by non-conservative forces. So I want to remind us of the equation for work, force dotted in to displacement. So those are two vector quantities and we need to consider that. Okay, so let's look at our scenario here. We have an armadillo sliding some distance d down an icy incline from rest. At the bottom, it slides onto a horizontal patch of ice. We're going to assume the transition is ideal and determine how much displacement is required for the armadillo to slide to a halt. So, what we know is at the top here of the incline that we know that the armadillo starts from rest. So we can say V naught equals 0. And then we know that the armadillo eventually comes to rest. V final is 0. This distance in here is given as D. That's one of our givens there. And we're also given, note the coefficient of kinetic friction between the armadillo and the ice. And that coefficient is the same on the incline as it is on the horizontal patch. And what we're being asked to find, what we're being asked for is how far this is right in here. We're being asked for that. And I don't know why I just call that S for now. Okay. So we need to start by dealing with looking at the left-hand side of our energy equation, and that is energy final and energy initial. So I'm actually going to call this spot up here right at the top right when it's released at 0, I'm going to call that my initial mechanical energy, and then I'm going to call this my final mechanical energy, where it's at the bottom and it's at rest. So let's see if I can write out what this means then. My initial mechanical energy, the armadillo's at the top. It's released from rest, so there's no kinetic energy there. But is there gravitational potential energy? Well, I guess it depends on where we define our y equals 0. So for this problem, I'm going to define my y equals 0 for the lowest point in the problem. That's often advantageous to do that and is somewhat intuitive. So I would encourage you to find the lowest elevation point in your problem. Just call that your y equals 0 and go from there. So if I do so, then I can see that the armadillo is raised up above 0 there, something I'm just going to call this H for right now. I know that this is a right triangle, so I can express H in terms of D and phi, and I'll worry about that later. So my initial energy is going to be mg h. That's it. There's no kinetic energy, no spring energy there. My final mechanical energy, this will be after the armadillo has come to rest. There's no kinetic energy. It's at the lowest elevation. There's no gravitational potential. There are no springs, no spring potential. So I don't have any mechanical energy left in my system at the end there. So the change in energy is final minus initial. So 0 minus mgh. That gives me negative mgh. That is the left-hand side of my overall energy equation. So this energy conservation equation is what is our guide through this problem. Now I'm going to go to the right-hand side of that equation, and that tells me that I have to start thinking about works here, right? So I'm going to, in order to think about works, I need free body diagrams, right? I know that. So I'll look at the armadillo on the incline. So I'll look at on the incline and I'll look at on the horizontal spot there too. And I need two free body diagrams. If you're not sure why, you will be in a moment here. The forces are different on the incline, right? Versus on the horizontal patch there. So we need to look at them differently. So on the incline, what is in contact with the armadillo? Just the surface beneath it. So that's going to provide a normal force upward and a frictional force that's opposing the motion. So frictional force is directed up the incline. And then of course I have the weight, my weight of the armadillo as well. Be sure to always label any off-axis angles. So I'm using a rotated coordinate system here, a coordinate system that is rotated so that it aligns with the surface of the incline. The horizontal patch, same thing. The only thing in contact with the armadillo is the surface beneath it. So again, and here I'm not using a rotated coordinate system. There's no reason to. Again, there's a normal force. And right now I'm going to pause because I don't want to use the same symbol for normal force on each of these diagrams, right? Because the same symbol indicates that it's the same quantity. So I'll just prime this one on the horizontal patch, indicating that it's a different quantity than the other normal force, or even if it's just possibly a different quantity, you want to use a different symbol. I have frictional force again when we're on the horizontal patch. And again, this isn't necessarily the same frictional force as on the incline, so I'm going to prime that as well. I have weight straight down now. We're not in a rotated coordinate system. My weight is the same. The armadillo's weight doesn't change depending on where it is on the incline or horizontal patch. Okay, and now because I'm going to be calculating works, I need to keep in mind the direction of displacement. So when the armadillo is on the incline, the displacement is in the direction that is down the incline. And when it's on the horizontal to the right is the direction of displacement. So I'm just kind of keeping those displacement directions in mind because I know that I need to think about the relationship between work and displacement when I'm sorry, between force and displacement when I'm calculating my works. So I'm going to go through and do my works real quick here. If I look at on the incline, I can see right away by inspection that the normal force doesn't do work. Normal force is orthogonal to the displacement and no work is done there. But I can see that I am going to have work done by the frictional force and um, I was going to say by the weight, but remember that the weight is a conservative force, and all we care about here are the works done by non-conservative forces. So on the incline, my two non-conservative forces are normal force and frictional force. So those are the only ones I would consider. Work done by normal force is 0 due to the fact that it's 90 degrees from displacement. So really the only non-conservative force that does work here is the frictional force. So I calculate that here. It's going to be equal to the magnitude of the frictional force multiplied by the magnitude of the displacement that's given to us as d on the incline, multiplied by the angle, the cosine of the angle between them, and that's 180 degrees here. They're in opposite directions. So the work done by friction on the incline is just going to be negative F sub k d. And we need to flesh out that F sub k. We know that. And write it in terms of the normal force and write it in terms of things that were given in the problem. But we can do that later. So if I look at the horizontal patch, I see that I have two non-conservative forces. Again, normal force and friction there. Normal force is orthogonal to my displacement, so it will not do any work, but the frictional force will do work here. So the work done by friction, I'm going to prime this since it's different from that done on the incline, is going to be the frictional force magnitude, Fk prime. Now, this displacement magnitude, this is the thing I'm trying to find in the problem, right? This is the whole reason I'm doing this. So here, finally, I'm getting my unknown on the page, the thing I want. I'm just going to call that S for right now. And then there's 180 degrees between those two vectors. So this work ends up being negative Fk prime times S. Okay, so really important that we had those two separate free body diagrams there, right? We get separate information from those. And it might be good to take a moment and just kind of figure out what those frictional forces are equal to. You'd want to substitute that in there. I'll change up my color and do that here. So the frictional, this F sub k, is going to be equal to mu sub k times the normal force, right? Which is equal to mu sub k mg cosine phi. Yeah, so that is that frictional force. On the horizontal patch, now I'm wanting to solve for Fk prime. That's going to be same mu k, but now multiplied by n prime, different normal force. So that's just going to be equal to mu k mg. So notice those, right? Those are different. Those frictional forces are different, even though the coefficient is the same, due to the fact that the normal force is different on those two different surfaces. Okay, so we've got that cranked out. We know that we can substitute that in. That's just algebra stuff. And we want to go back. I want to kind of take us back to the arc of what we're doing, which is focusing on our conservation of energy equation. So our conservation of energy equation tells us that the change in mechanical energy is equal to the sum of the works done by non-conservative forces. So let's put that into practice here. The delta E side, we already calculated that. We did that first. That's equal to negative mgh. And now on the right-hand side, let's sum up the works done by non-conservative forces. So that is going to be on the incline, I'll have negative mu k mg cosine phi multiplied by d. And on the horizontal patch, I'll have negative mu k mg multiplied by s. S is the what I'm going for, right? It's what I'm looking for in this problem. S is what I want to find. So I can kind of look at this and say, oh yeah, I can multiply through here by -1, get rid of these negative signs. I also see that every term in here has an M, so I can get rid of that. I see that every term in here has a G. I can get rid of that and see what I come up with here first pass. H is equal to, remember I'm multiplying through by -1, so I drop all the signs for all the terms here. Mu k d times cosine phi plus mu k s. S is what I want. So, right, I want to get that one by itself. H, oh, and then H, of course, is not written in terms of what we know. So let's look at our H for just a second up here. H is equal to, I'll do that inside this thing here. So look at H, you can see that that's equal to D sine phi. So I'm going to go ahead and substitute that in there now. So that would be D sine phi minus mu k d cosine phi. That allows me to solve for S. D quantity sine phi minus mu k cosine phi all over mu k. Okay, so that is, and there, different ways you can write that out, but that is what this question here is asking for. So this is a good problem. I like it because it starts getting into a little bit of complexity here, and reminding you how much this course builds on itself, right? Like it's assumed that you've got the friction down, you've got the incline down, you have down these skills that we have built. You know how to calculate work in previous chapters, and you're putting that all together and synthesizing it in a problem like this one.